Okay, so it's time, so I'm gonna start. I'm Jun Nakajima from Intel. Um, I've been working on virtualization for a while, for years, actually almost a decade. And I guess some of you, know me for years as well. I've been working on general virtualization, means the stuff you guys working on, right? Those are used for data centers and cloud and desktop, laptops everywhere. Now recently, NFV network functions virtualization and also SDN, software defined network, are becoming very hot, even like a buzzword. But it's kind of buzzword, but it's interesting topic, and it is one of the area that should grow over the years. So today I want to talk about that, how we make Xen as a high performance NFV platform. Okay. I'm going to start with the what's NFV, network functions virtualization first, and then talk about the characteristics of a workload from a virtualization, base virtualization's perspective. Okay, not from the contents. Yeah. And then new or different requirement from for NFV, then challenges and the solution, and then I want to propose architecture for NFV on Xen, and followed by summary. Okay. So first of all, NFV has been proposed by ETSI. ETSI is a European Telecommunications Standards Institute. The key word here is, first of all, telecommunications. Okay, so these are coming from telco guys, not the data center guys. Okay, and if you're interested in the more details, look at the URL, and you can get the white paper, so you can get the more details. What they are talking about is basically the classic network appliances approach is not sustainable. Okay, there are a bunch of different hardware and then fragmented, and those are sorry, implemented on a non-commodity platform. What they are proposing here is, instead of those using those fragmented hardware, use a software virtual appliances, and use orchestration or automation, and then run those on high volume servers or high volume platform. Okay, that's what they're proposing, and the vision, what their vision is. It doesn't mean this is implementable. Okay, so this is what they are asking for, and as you see, there are challenges there. Okay, so I'll talk about challenges, and before going to the challenge, let's take a look at high-level workload of NFV. This is very high level. I don't expect you to, understand the low-level things yet. Okay, I'll go there later. But at the high level, first of all, I think first thing I need to mention is their view from a telco guy's point of view. Their priority is the wire. Okay, unlike ours, we are focusing on like a servers, a computation, but their focus is the wire. That's their asset, actually. So from their point of view, NFVs, those components, are bumping the wire, okay? So anyway, the key is the wire, so their focus is wire, and one of the key characteristics is very high I/O rate. I'm not talking about interrupt, but they tend to use high-end, Ethernet, like a 10 gig, a 40 gig, very high bandwidth Ethernet, and not just one, but multiple of them. And then the size of packets are also important. The packets we deal with are typically big, but in that case, they need to support all sizes of packets, large ones and small ones. Small ones, for example, like a 64 byte, okay, 64 byte, okay, not the K, okay. So it's very small. And then each box, sometimes they called middle box or virtual appliance. Okay, I may use either way in this presentation. Okay, and some of them have very compute intensive. Okay, for example, deep packet inspection. Probably they are consuming lots of CPU and memory. Okay. And then after processing packets, those packets are sometimes or oftentimes routed to other middle boxes. Okay. For example, firewall or load balancer or routers. And when packets are sent, they typically use a vSwitch. vSwitch is just a virtual switch. This is just a functionality I'm talking about. Okay. So anyway, this is a kind of a high-level view of NFV workload. So just summarize. This is very high-level summary of requirements. First of all, high performance across all the packet sizes, including small packets. And this is actually the problem, the small packets. 64 byte means 8 words in 64-bit, okay? And real-time processing, when we say real-time, it just includes low latency and jitter as well, and RAS and security. I'll talk about more on those. So in terms of supporting NFV, those are the areas we need to take a look at. First of all, obviously network I/O. Like I said, 10 gig, 4 gig, 40 gig, and direct I/O. If we use a PBA, sometimes it's hard to get very high performance. So in order to get the high performance, we need to use a direct I/O, SR-IOV or VTD, and there is some technology called a data direct I/O. This one is basically the packets from NIC are copied directly to CPU cache, not the memory. So that the CPU can then process the data descriptor while they are in cache. Okay. And the interrupt virtualization, I'll actually talk about the interrupt virtualization post-interrupt tomorrow, so I skipped this one. And the computing side, the CPU affinity, NUMA stuff also important. Okay. and the real-time RAS and the security. The last two actually, those are actually very generic. So I don't talk about the details of those today. So I'm going to focus on the last two things, guests themselves, and then inter-VM communication. Okay. So this is a detail about handling small packets in gas. This is a Linux, and we feed very high traffic using a traffic generator, sending 64 bytes, okay, using a 10 gig Ethernet. At the device level, we are seeing line rate, which is 4.8, 14.8 million per packet per second, okay. And then at the device driver level, it's significantly reduced, okay, like 3.7 or something like that. And if you going up to the Linux kernel, it's 1 million packet per second. Then as you go higher to finally to the user process, it's even less than 1 million packet per second kind of performance. Okay. So the issue is the Linux software stack and basically software stack. If you imagine, you know, like I said, it's 8 words. 8 words, 64 byte, right? If you code a function, typically you need to save the contents of registers, right, into stack. How many bytes you save typically? That kind of question, right? It's possible you save more than 64 bytes in stack if you just call a function with many arguments, for example. Okay. I have a good news and bad news here. So good news. Good news is if we do the same thing in virtualization, okay, that was bare metal, okay? And then this is a virtualization with a VTD, direct assign, same guest, basically. Good news is we have basically same performance. So we don't have a very visible performance regression because of virtualization. That's good news, okay? So what is the bad news? Bad news is we cannot help here. Basically, we need to fix the guest, you know, to get the good performance, right? Okay. So the network stack in VM, this is a Linux, can have a big performance bottleneck. So the other topic is inter-VM communication, especially a switching path. So when we send a packet from one to another, there are many things happen. One thing you need to take a look at is this number, this one. Remember, this number was more than 3.5 million in this, you know. In this picture, this is, you know, in this configuration, sorry, let me back up. This configuration is different from the previous one, okay? Here, they are running in, on top of a KVM, actually, with the BROT.io and vHostNet, which should have optimal, you know, performance, or in other words, minimal overhead, okay? But to send a packet from one VM to another, there are many things needs to happen. And because of those overhead, the performance is even, you know, lower, okay, in this case. So the switching code path is very important and can be a bottleneck here. Based on our analysis, typically the root cause or the bottlenecks are, for example, the control for the notification. For example, Virtual.io has a notion of a kick. Okay, so for example, the length of a queue reaches the, for example, watermark, then the Virtual.io generate kick event, which is actually VM exit to the host KVM, so that the vhost can take the packets into the, move the start the code path, the tab to switch the tab, that kind of code path. As long as it's not so frequent, that's not harmful, of course. But remember, we are handling 14 million packets. Okay, of course we can batch. Okay, let's say we batch them. So based on data, typically VM exit happen like once per 10 packets. Okay, in that case, we still have 1 million, more than 1 million VM exit per second, and that easily can kill the performance. Okay, and the virtual switch cost, and also the other thing is a packet handling. Anyway, so this code path is also a bottleneck. Okay, so this is a recap. So in any case, if we have a problem with a guest, if the guest is not good, there's no way from our point of view, they need to fix the guest. And there are some solutions. For example, bypass the OS stack. Intel has, for example, DPDK. And then basically what it does is skip all the kernel stuff and do the job in user level. So the user level program has the device driver, okay, and the user polling, okay. So it doesn't use even interrupt. So this is that then it can achieve like a line date, okay. Now I'm talking about the inter-VM communication next. So before that, why the inter-VM communication is important? One of the reasons is we're going to have more cores in a socket on a server. I mean, on server. For example, this is the latest socket Xeon chip from us, and then it's Ivy Bridge. Xeon, Ivy Bridge based on Xeon, which has 12 cores in a socket. And I know we're going to have more in the next generations. So that means we have more middle boxes, right, in a socket on the same node. Okay. Then telco guys have a notion about service chaining. So packets of water to different middle boxes depending on the function. Right? So they are also they can be also in the same box. So that basically means inter-VM communication. Okay. Then we have a kind of motivation. First of all, it's the latency. If you compare the latency inter-node versus intranode, you should have much lower latency within the node, which is the intranode, right? So if we can have other middle box in the same node, then you can have a lower latency. The other reason is higher bandwidth. Okay. If you compare PCI Express bus versus the memory or interconnect bandwidth, obviously that memory bandwidth and the QPI bandwidth are higher. Okay, so this is the reason inter-VM communication will be very important. So let's take a look at existing solution and with issues. So one of the simple things would be use SR-IOV VFs with virtual Ethernet bridge. Virtual Ethernet bridge are, some NICs have built-in a simple switch functionality, and the problem is the limitation of functionalities in VFs. So VFs, the virtual functions, a simpler version of a VF, physical function. Okay. Those limitations actually have impact to the performance. Okay, so sometimes you need multiple VFs you need to assign, right, multiple VFs to a single middle box to get the good performance. Okay, that's one thing. Other reason is the functionality is not good enough to handle the switching or handling a different type of packets, for example. So oftentimes they need to fall back to software actually. So you don't get the good performance in that case. Okay. Shared memory. So shared memory will be reasonable because for example, bandwidth reasons, for example. But if we use same notification like VM exit or interrupt for doorbell or kick event, like I said, right? So those can be very frequent depending on size of packets and the frequency. And we cannot handle 1 million VM exit per second. That's impossible. Okay. So we really need to change the notification mechanism. Okay. I'll skip the V switch, but the security issue. If VMs are sharing pages and all the packets for the VMs are, visible there, people have a security concern because anybody in the VMs can take a look at any packet, right? So that's a bit scary. Okay. And sometimes other VM can corrupt, data, for example. So to avoid that kind of situation, sometimes, depending on the implementation, some implementation actually copy data to the shared buffer, for example. Okay, and that has security, not performance issues. So I've been thinking about the solution. How can we solve this kind of thing? So for Xen especially, one way is avoid hypervisor intervention as much as possible. Okay, what it means is move knowledge or control for inter-VM communication to the VM side, not not within the hypervisor side. Then allow VMs to share the key data structure like a queue or the in volatile case ring descriptor or something like that. Okay. Then use faster communication, so avoid interrupt the VM exit. Use not the porting. For example, we tested the monitor on M8 and actually work in 2 VMs, for example. Today, we disable this one. We don't advertise monitor M8 to the guest side. KVM does, but it's virtualized. But we can enable this in a native fashion, basically kind of pass through. Okay. Then monitor and emulate actually works between VMs or more than 2 VMs. Then allow VMs to access shared memory or guest memory in a safe way. So how can we do that? I'll talk about this protected memory view. Okay. I have a more detail on the protected memory in the next page, but I just explained the meaning of protected here. So with this memory view, one guy or more trusted guy, actually we need a trusted guy here, can see additional pages. Those pages can be shared memory or guest memory, but the key here is the mapping itself is protected by hypervisor. So even though we trust that guy, but the guy cannot change the mapping. So it's protected by the hypervisor. Okay. Only thing guest can do is just use that view. Okay. So we have a new hardware feature. It's been actually in SDM for a while. Okay. It's called EPTP switching. EPT is extended page table. I think many probably, I don't know. Do you know EPT, right? Essentially, what it does is convert guest physical memory to host physical memory. That's yet another mapping from virtual to physical in virtualization, right? So in this picture, let's say this blue, oops, this one is original the guest memory assigned to the guest. Then we add this protected view, means guest physical pages. Okay. Now the default EPT, if the default EPT doesn't have a translation from guest physical to host physical, and if somebody is trying to access the guest memory, okay, that would cause EPT violation. Okay, I'll talk about the hash V later, so you can ignore it. But if we have yet different EPT which has a valid translation to the shared memory or guest memory, okay, if we switch to that view, then the guest can see the contents of a guest view or shared memory. Okay, and the instruction for this is so-called VM func. Okay, we have VM func 0, and this is available in user only, basically in guest only. Okay, and it doesn't cause a VM exit. Okay, I'll have more detail on the next page. And this is available even in the user mode, Ring 3. Okay, it sounds like a dangerous, but mapping must be done again hypervisor. Okay, so this is a detail of a VM func. So VM func 0 is EPTP switching. Okay, and 0 means we set the EAX to 0. Okay, and the ECX point to the index in the EPTP list, which is a 4K byte, and this is pointed to by VMCS. Okay, so if the guest does VM func with 0 and the index, then upon that instruction, this EPT will be used. Okay, and again, no VM exit, and the TLB should also work well here. And if it's if the feature is not there, we can actually virtualize this one. Okay, we need to take a VM exit in that case. But if we have a, you know, different alternative EPT, we can switch to this one easily. So hash VE is so-called virtualization exception. This is also in SDM today. This happens only in guest. Okay. The idea is basically convert some EPT violation to basically bounce back, you know, without causing a VM exit. You know, EPT violation is VM exit, right? But if guest itself want to know about, you know, handle efficiently, then it can take a hash VE. So if guest try to access some memory that EPT doesn't have a permission, then causes hash VE in the guest. Okay. So this is the example. So hypervisor needs to do something for this, of course. So the guest needs to ask the requester hypervisor to map additional memory. Okay, this is a very simple example. Okay, just you know, show how it works. So it's not really trusted way or anything. Okay, so basically ask a hypervisor to create alternative memory, and then, you know, for example, specifying a target domain ID. Okay, then it returns the index of a, you know, EPTP list. Okay, then there, once VM-func is done, then it can access the protected view. Okay. Then he can do whatever he wants. Okay. Once the job is done, then it's up to him. He can actually close this one by going back to the default EPT. Okay. So I have a architectural proposal for NFV on Xen. Okay. So a bit busy, but first of all, this is a middle box, and let's say the vSwitch function is here. Okay. Now this is a protected view. Okay. VM1 in this case has a grant table. Okay. Then basically tell which pages can be visible in the protected view. He can specify using grant table. With VM2, entire VM will be shown to the either way. And once the middle box does a VM-func, the contents or the pages of the VM1, you know, in this case, the page is granted. And VM2 case, all the pages of VM2 are visible in that view. Okay. Then, of course, the location of queues and the key data structure must be, you know, exchanged prior to this, or this is outside scope of this one. But you can, for example, they can exchange that kind of information where the, for example, queues are, where the size of ring buffer, whatever. Okay, very similar to our back end and front end mechanism. Okay, So if we have this one, so let's say if we forward a packet from VM1 to VM2, okay? In the protected view, it's very simple. He just copy, right? Doesn't show anything. Okay, just like this. Then if he copies a, for example, small data like a 64 byte, and actually the data copy from here to here, right? So then it says kick doesn't cause a VM exit, means we don't use a VM exit, but use monitor and M-wait for notification. So we look at some variable that describe the state of that, the queues. Okay. That way we can avoid. Sorry.
Clarifying question. So the vSwitch VM can see the memory of both VM1 and VM2 at the same time.
That's right.
Okay.
Yes.
Is there a limit to how many VMs a third VM can see? I don't know what time is it, 2 or many?
It doesn't matter, right? Yeah, it's the limitation will be probably the size of virtual address.
Okay, right.
Or physical address. Yes.
Cool. All right, thanks.
Yeah.
So you just said that you don't have to, you don't use interrupt to notify the buffer the queues. So you just use polling from the down
Polling, you could use a polling, but I don't recommend a polling because of energy issue, because you keep looping at the full speed, right? So you waste energy. So instead, better way will be use a monitor and M-wait, or at least a pause loop kind of thing. You check and do pause, kind of a looping. Any question? That's a good question. So the major reason is kind of security or limit that does visibility as much as possible, because within that middle box you may have other code that do other things, right? So if we can limit the scope to only particular code sequence or only the process, then this is a bit dangerous operation, right? So that's a reason if you expose open all the time, or if you open to other process or anybody, then like I mentioned, there are security concerns there.
But in the end, with VM5 being available even to ring free, everyone can do this at every time.
That's not actually true. There are the ways to prevent, and we can allow only limited trusted guys. I don't cover that one. We can discuss later. Okay. So the example I showed didn't cover that one, but there is a way to do that in a secure fashion. Actually, the VM-Func was, I think, invented for security, implement a security feature. Okay. So if we use BTD or SRB device, actually, we can copy packets from to VM1, because this machine address of a VM1 is also visible in this the protected view. Of course, in this case, you need to program BTD as well. Okay.
And does VM front do the switching for
No,
just EPT?
at this point, no.
Yeah, how are you going to do that? That, I mean, you have to share the table and the EPD and the so you have to share the table with the EPD.
Today, yes. So if we use a default VTD table, then this doesn't work. So once we create the EPT, then extend it, then if that VTD use that new EPT and share, then this should work as well. In that case, the VM func doesn't affect the VTD side, right? As long as we keep that VTD, it's always visible to VTD. Okay, so this is the benefits of new architecture. I think I should be run through this one, but in this architecture, we can contain that the knowledge of the control for inter-VM communication in the VM side. Okay, by doing this, we can keep hypervisor simple and thin. Okay, and this actually suitable for Xen, hypervisor architecture based, like a Xen. And I guess this is better than vHostNet. Main reason is vHostNet by the inherently needs to depends on the Linux network stack. Okay, network stack. So if he wants to do something different, something differently, he has no freedom, or he has no way to optimize. But in this case, if this is in the guess and it's up to guess, you can write more efficient, queue control or copying, whatever. That's up to the guest. Okay, so this can be more powerful. And we can minimize overhead, and then so then it works with direct I/O. Okay. This is current status. The patches for the EPT switching is and #B for Xen is being reviewed, and then if you are interested in those, we have a Robbie, so ask Robbie there. And so this is coming. Yeah. Essentially, it adds alternative EPT given domain, basically. Okay. Then what I'm looking at is combine this with the page flipping. Okay, the problem is page flipping is the invalidation of a TLB. Okay, and then that's very costly. And for EPT invalidation is also costly. So what I'm looking at is basically amortize the EPT invalidation. Basically, how do we do that? Basically, the hint is, we don't need to invalidate EPT as long as we just create new translation. If previously it was not valid, then if we add valid translation, at that point we don't need to invalidate EPT. Okay. Then I will take a look at basically measuring performance at this point. So this is my end of my presentation. And yeah, any more questions?
How did ETSI come up with the base values for what's expected? Are the expectations set right now, or are there no expectations for
Um,
And if there are metrics, I'm curious how they're determined.
there are, I think, internal thing and external thing. So I'm not sure, but
Not sure what you can say.
yeah.
I understand.
But I really recommend read the white paper first. Then my point here is I think they don't like the existing approaches, and they really want to switch to the nicer, more advanced and new, solution based on virtualization, right? But they haven't implemented. They haven't data. They don't have a POC or anything, right? So they just ask for or proposing how it works or not. And as you see, there are lots of challenges from virtualization point of view, hypervisor's point of view.
So basically, maybe meet the current expectations for current
If we simply just build and put middle boxes on top of Xen and it doesn't function at all, I don't think that we can meet a performance requirement. We miss probably 10x or 100x slower.
But you did mention it's solved using Intel DPDK.
Right. So if we use DPDK and do those in all user level without interrupt, that would work. Yes, but they need to rewrite their middle boxes, everything basically. So for limited situation, yes, they can rewrite and use DPDK, whatever, yeah, and combine with Open vSwitch and DPDK, something like that. So they can do that.
No, the embedded mechanism can also be currently used for any query protocols. You could use it instead of application system.
Mm-hmm.
Okay. Is there any plans to make something out of that as well or no?
We are looking at right now. But, first of all, it can have some again security issue. It really enters the some C state. So this is a reason, also that only maybe trusted guy. We need to allow trusted guy to enter, use a monitor and M weight, real monitor and M weight. Yeah, especially M weights.
So it sounds like this, in sort of NFV aside, the EPTP mechanism sounds like it could be a very generally useful thing for any user space process to access another domain's memory.
Yeah.
Are you looking at things like applications maybe in QMU and other things that run in DOM 0 or drive commands? Could those be possible applications?
If you can, yes, trust, that's possible, right? It's up to hypervisor, because you basically allow him to access beyond that the usual view, right? You initially provided. So
That should allow us to remove a whole bunch of backend drivers.
Yeah.
yeah.
Potentially in a more scalable way than graph tables.
Yeah.
Is it necessary? But that's a separate question.
Mm.
You mentioned something about direct cache DCA,
Oh,
and I think that's also called Intel.
DDIO.
Yes, that's correct. Does any of the two guys, does the VFunk, are you guys also utilizing this in your testing to kind of,
DDIO is automatically enabled.
that is, okay.
Yeah. By default, it's there.
So is that the same thing as the Intel IO AP? Or could the Intel
Yeah, I think it's a,
The
fu-
same acronym.
yeah.
Realtime.
But now I think it's more useful. I think before that, I think that the driver needs to do something,
Right.
right? Here, you don't need to do anything. Just the hardware automatically does that.
For the automatic stuff.
Yeah.
You mentioned that it's zero copy. So I understand that we will be zero copy with the communication, external communication. But on the end-to-end with the end communication, at some point, there needs to be a copy, right?
Oh yes. What I meant was you don't need to copy to buffer. You know, I mentioned that security issue, right? So some implementation, like a shared memory implementation, they actually, even with a DPDK, you know, can work with shared memory. In that case, they copy data to the shared memory.
Right. I see.
Okay. We can avoid that copy, and that's what I meant.